Okay, let's unpack this. Imagine looking at your online bank account, sending a private message, or even just, browsing a secure website. Knowing that every piece of data, every carefully crafted encryption could someday be effortlessly unzipped.
Hmm.
Not by some super hacker today, but by a computer from the future, a machine so powerful it could unravel decades of digital trust, making even today's secure communications transparent. That's the looming shadow of quantum computing, and, well, for the world of digital security, it's not some far-off sci-fi plot anymore.
No, it's a very real prospect.
Right.
And what's truly fascinating here is how the global cryptographic community isn't just bracing for impact. They're proactively building the next generation of defenses.
Right.
This isn't a scramble for a last-minute patch. It's a monumental collaborative effort. Our deep dive today is into lattice-based cryptography. It's a field offering not just resilience against these future quantum attacks, but actually a whole new paradigm for digital security that promises to be incredibly robust and versatile.
Our mission, then, to take you on a clear, engaging, and I hope surprisingly fun journey into this world of lattices. We'll explore everything from these hidden, high-dimensional mathematical grids to the powerful algorithms they enable, the ones poised to protect our most sensitive data. We'll demystify not just how these abstract structures provide such profound security, but maybe more importantly, why you should care about this crucial and rapidly evolving area. Think of this as your essential guide to understanding the strategic importance of these quantum-resistant algorithms. Hashtag the quantum threat and the dawn of a new cryptography. So let's start with the problem that really set this entire race in motion. For decades, our entire digital infrastructure, the very fabric of the internet as we know it, has relied on what we now call classical cryptography. We're talking about systems like RSA and elliptic curve cryptography, ECC.
The bedrock.
They really are the bedrock of modern security. Every secure website you visit, every encrypted email, every digital signature confirming a document's authenticity, they all lean on the computational difficulty of certain math problems for regular classical computers.
Precisely. Take RSA, for example. Its security relies on the sheer impossibility, really, for any current classical machine, of taking a truly massive number and factoring it back into its two prime components.
It's like being given a giant cake and having to figure out the exact recipe instantly.
Kinda, yeah. Or like being given a huge, complicated product and needing to find the two secret ingredients that created it. For something like a 2048-bit RSA key, this task would literally take a classical supercomputer.
Right.
Well, they estimate trillions of years.
Trillions, okay.
That staggering amount of time makes it effectively impossible to break. Secure. This computational asymmetry, easy to multiply two primes, practically impossible to find them again from the product that's been our digital shield.
And it's been a brilliant shield, but what happens when a completely new type of computing power enters the scene?
Well, that's where quantum computers introduce an existential threat, a really fundamental one. Unlike classical bits, which are just a 0 or a 1, quantum computers use qubits. And these qubits can exist in what's called a superposition.
Meaning 0, 1, or somehow both at the same time.
Exactly. And then you add entanglement to the mix, where qubits become linked, sharing properties no matter how far apart they are. This combination lets a quantum computer explore a vast number of possibilities in parallel. It's a way classical computers simply can't operate. It's not just a faster computer, it's a fundamentally different way of processing information. It represents a seismic event for computation.
And the really unsettling part of this isn't just about some distant future threat breaking things later. It's this idea, what security experts call the harvest now, decrypt later scenario.
Yes, that's crucial.
Think about it, the data you encrypt today, maybe your most sensitive personal info or national security secrets, it could be intercepted, harvested, and just stored by malicious actors, quietly.
Just sitting there waiting.
Exactly. Then, in the future, maybe 5, 10, 20 years from now, when sufficiently powerful quantum computers become available, all that previously impenetrable data could be instantly decrypted. Your secrets, even if they've been locked away for years, would become completely transparent. It really makes you look at your cloud storage or past emails differently.
It certainly should.
Knowing something you're encrypting today could be exposed years down the line. So what does this all mean for the security you rely on every day? Every secure connection, every encrypted message potentially vulnerable, not just tomorrow, but from data collected today.
That chilling prospect is precisely why Peter Shor's 1994 breakthrough sent such shockwaves through the cryptographic world. Shor's algorithm is a quantum algorithm specifically designed to attack the mathematical problems underlying RSA and ECC.
The factoring and discrete logarithm problems?
Exactly those. The
Yeah.
very foundations.
So, okay, classical computer needs trillions of years for RSA 2048. What could Shor's algorithm do, theoretically?
On a sufficiently powerful quantum computer. And that's a big if for when. But the theory holds it could theoretically break that same encryption in a matter of hours, maybe days.
Hours or days versus trillions of years, that's hard to even grasp.
It's exponential speed up. And it's not about guessing faster. It leverages quantum mechanics to find entirely new mathematical pathways to a solution.
But how does it do that? It's not just brute forcing all possibilities, right? That sounds like what a classical computer does, just faster.
You're absolutely right. It's far more sophisticated. Shor's algorithm cleverly transforms the problem of factoring large numbers or solving discrete logarithms into something called a period-finding problem.
Period finding, like finding a pattern.
Essentially, yes.
Yeah.
Imagine you have a really complex, repeating wave pattern hidden in a huge amount of noise. Classical computers are terrible at quickly finding those hidden periodic structures in massive data sets. Quantum computers, though, with their ability to be in multiple states at once and using a tool called the quantum Fourier transform, are exceptionally good at discovering these hidden rhythms.
So they can hear the underlying beat that classical computers miss.
That's a great analogy. It's like they can instantly see the rhythm in an overwhelmingly complex musical score that classical machines would struggle to pick out note by note. The implications are, as you said, catastrophic. Secure communication becomes transparent, digital signatures become untrustworthy, the entire financial system, banking, crypto, it all faces fundamental compromise.
It really breaks the model.
It does. This isn't just about faster calculations, it's a fundamental shift. Problems, once deemed intractable, become solvable. And this raises that critical question. Can we find new mathematical foundations, new problems that resist this kind of quantum exploitation?
Okay, Shor's algorithm is definitely the big, scary monster for asymmetric crypto, the public key stuff. But there's another quantum player people talk about, Grover's algorithm. You called it a lesser threat, but still significant.
Yes, Grover's algorithm, developed by Love Grover in 1996, offers a quadratic speedup for unstructured search problems.
Unstructured search, like finding a name in a phone book that isn't alphabetized.
Exactly like that. Trying to find a specific item in a completely unsorted list where you have zero clues about its location. A classical computer, on average, would have to check about half the list entries, and 2 checks. Grover's algorithm, however, can find it in roughly the square root of the total number of items, square root of n steps.
Okay, square root. So if your list has, say, 1 million items, classical needs maybe 500,000 checks on average.
Well, Grover's could potentially find it in about 1,000 checks.
That's still a massive speed up. So what does that mean for our symmetric encryption? Things like AES, which we use everywhere for bulk data encryption. Does Grover's break that too?
Thankfully, no. Not in the same way Shor breaks RSA. Its impact on symmetric crypto, like the Advanced Encryption Standard, AES, is considered manageable. AES relies on the infeasibility of just trying every possible key brute force search. Grover's algorithm doesn't break AES, it only weakens it. For example, if you're using AES 128 with a 128-bit key, Grover's effectively reduces the security level to that of a 64-bit key against a quantum attacker.
Which is not good. 64-bit is breakable today.
Right. But the fix is straightforward. To maintain the original 128-bit security level against a quantum attacker, you simply double the key length. You move from AES 128 to AES 256.
Oh, I see. So it forces an upgrade, but the algorithm itself isn't fundamentally broken.
Precisely. It requires an adjustment, doubling the key size, but it doesn't unravel the core algorithm. That's why we say Grover's threat is manageable, unlike Shor's fundamental impact on public key crypto, which would completely shatter RSA and ECC.
So faced with Shor's existential threat and Grover's significant weakening effect, the world's cryptographers weren't just sitting around waiting for the quantum sky to fall. What was the plan? How do you fight back against something like Shor's?
That's exactly where post-quantum cryptography, or PQC, comes onto the scene. Its mission is absolutely critical. Develop cryptographic algorithms that are resistant to attacks from both classical and quantum computers.
Okay, post-quantum. Meaning, after quantum computers exist, these should still work.
Right. And it's crucial to understand, PQC doesn't use quantum mechanics for its security. That's a different field called quantum key distribution, QKD.
Good distinction.
PQC instead seeks entirely new mathematical problems. Problems that are believed to be hard for all computational paradigms we know, including these powerful quantum ones. To accelerate this, the U.S. National Institute of Standards and Technology, NIST, initiated a really rigorous standardization process back in 2016.
The famous NIST PQC competition.
Exactly. They launched a worldwide competition soliciting and evaluating candidate algorithms from various mathematical families: lattice-based, code-based, hash-based, multivariate, isogeny-based, a whole range of approaches.
Wow. So this wasn't just a casual call for papers. This was a multi-year, multi-round gauntlet. Cryptographers worldwide trying to break each other's algorithms, essentially a global cryptographic thunderdome.
That's a pretty good description.
Yeah.
And after all that intense scrutiny, years of analysis, in July 2022, NIST announced its first set of standardized algorithms.
And the results were?
The overwhelming winner really was lattice-based cryptography, which leads to the obvious question.
Yeah, why lattices? What made these abstract mathematical grids the unexpected frontrunner in this critical race to secure our digital future?
It really comes down to a powerful combination of factors. But, to get an info feel for it, let's go back to that analogy of a tiled floor.
Okay, the grid.
Imagine the intersections on that floor. In 2D, if you step slightly off an intersection, finding the closest grid point is trivial, easy. But now, try to visualize that grid not in 2 or 3 dimensions, but in 500 dimensions.
Yeah.
Or 1,000. It's a structure so vast, so complex, our brains just can't visualize it.
Impossible to picture.
Right. And if you're given a point that's slightly off the grid in this impossibly high-dimensional space, and you need to find the closest actual grid point, that problem known as the closest vector problem, CVP, becomes incredibly computationally hard. Even for quantum computers, there's no known clever trick, no shortcut like Shor's algorithm exploiting hidden structure. It's more like a messy geometric search through an astronomically large, utterly bewildering space.
So the sheer complexity, the geometry of these high-dimensional grids is the source of their strength. But what are the specific advantages that made them stand out so much to NIST?
Well, there are 3 main ones, really compelling advantages. First, strong security. They're based on these well-studied mathematical problems like SVP and CVP, for which no efficient quantum attacks are known. The best algorithms we have, classical or quantum, for solving these lattice problems have runtimes that grow exponentially with the number of dimensions.
Meaning if computers get faster, you just add more dimensions.
Exactly. We have a clear path to stay ahead. Simply increase the number of dimensions in the lattice makes the problem exponentially harder, ensuring long-term security. It scales well against attackers. Second, they boast remarkable efficiency. This might be surprising, but lattice schemes are relatively fast on modern hardware, often outperforming even existing classical systems like RSA or ECC for certain operations. That makes them practical for real-world use.
Bigger keys, as we'll see, but faster operations sometimes. Interesting trade-off.
It is. And third, they offer incredible versatility. The underlying math lets us build a whole range of crypto tools: public key encryption, key exchange, digital signatures, and even advanced, really groundbreaking concepts like fully homomorphic encryption.
We'll definitely get to FHE later. That sounds amazing.
It is. And other post-quantum candidates really struggle to provide that kind of versatility. So strong security, good efficiency, and this amazing versatility. That combination is why lattices emerged as the clear frontrunner. #tag mathematical foundations. What is a lattice?
All right, so we're building our digital future on these high-dimensional grids, but let's get fundamental for a moment. What is a lattice, mathematically speaking? My brain goes to, a garden trellis or the lines on graph paper. Is that a decent starting point?
Absolutely. That geometric intuition is key. A lattice is a regular, repeating arrangement of points in space. Think of those precise, ordered intersections on graph paper, or maybe the atomic positions in a perfect crystal structure. More formally, though, a lattice is the set of all possible integer linear combinations of a set of linearly independent basis vectors.
Okay, integer linear combinations of basis vectors. Break that down.
Imagine you have a few fundamental vectors like directions and distances. Let's call them math BSB1, math BFE, up to math BFBS. A lattice point is simply any location you can reach by starting at the origin and adding or subtracting these basis vectors, but only using whole number amounts of each.
So like 3 steps along math BFB1, minus 2 steps along math BFB2, plus 5 steps along math BFB3, but never 3.5 steps.
Exactly. Only integers. So a point math BFX is new math BFX, way I1 math BFB1, plus I2 math BFB2, plus xn math BFE, where each $6 is an integer, positive, negative, or 0.
Yeah.
We often bundle these basis vectors as columns in a matrix, the basis matrix math BFBC.
So it's like using a specific set of building blocks, but you can only use whole numbers of those blocks, and you can build out infinitely in all directions defined by those blocks. But then you mentioned, for crypto, we're talking dimensions 1 gek, 200 and 500 and $66 says. How do we even wrap our heads around that? We can't visualize beyond 3 dimensions.
You can't, and that's where the math takes over from the visual intuition. You can't picture it, and that's precisely part of its strength, cryptographically speaking. While the 2D or 3D analogy helps grasp the idea of a structured grid, the mathematical properties, the rules for combining vectors, measuring distances, remain robust and become incredibly powerful in these high dimensions. The sheer number of possible pathways and points becomes astronomically large. It's impossible to brute force or navigate intuitively. The math works even when the pictures fail.
Okay, that makes sense. Which leads us to what you called the core secret, or the secret sauce of lattice crypto. This idea of good bases versus bad bases. That sounds intriguing, like a hidden passage.
It really is the ingenious trick at the heart of it. Here's the key insight. A single lattice, the exact same grid of points, can be described by many, many different sets of basis vectors.
Different blueprints for the same structure.
Precisely. Imagine our simple 2D grid again. A good basis might be the vectors 1, 0, and 0, 1. They're short, they're perfectly orthogonal perpendicular to each other. They clearly reveal the simple, ordered structure of the grid. This good basis is what we keep as our private key, our trapdoor. It makes the lattice structure obvious, making hard problems on that lattice easy for us, the legitimate users who know this basis.
But then you can have a bad basis for the exact same lattice. How does that look?
Right. For the exact same infinite set of points, you could find 2 very different basis vectors. Maybe very long skewed vectors like, say, 31 out of 15 and 17 and a half. No, these numbers actually generate the standard grid too.
Wow, okay. I would not have guessed that.
Exactly. If you were only given those 2 long, non-orthogonal vectors, it would be almost impossible to tell just by looking that they generate the same simple square grid as 1, 0, 0 and 0, 1. This bad basis is what we publish as our public key. It mathematically describes the lattice, allowing others to interact with it, like encrypting a message relative to it, but it completely hides the underlying easy-to-use structure. That structure is only revealed by the private key, the good basis.
So the attacker sees this complicated, messy-looking public basis,
making the hard problems on the lattice appear truly intractable to them.
So the same exact grid can look completely different depending on how you describe it. You publish the confusing, hard-to-use version, and you keep the simple, easy-to-use version for yourself. That's truly an ingenious way to create a secret. Does that mean the bad basis essentially scrambles the lattice in a way that's mathematically irreversible without the good one?
That's precisely the goal. The bad basis makes it computationally infeasible, we believe, to recover a good basis or to solve certain problems directly that would be easy with a good basis. It creates a one-way function, effectively. This brings us right to those hard problems.
Well, what are these specific hard problems? The ones that are easy with a good basis, impossible with a bad one.
The security of almost all lattice-based schemes rests on the presumed intractability of several core problems. The most famous one is probably the shortest vector problem, or SVP.
Find the shortest vector. Sounds simple enough.
The concept is simple. Given a basis for a lattice, usually a bad one, the goal is to find the non-zero vector in that lattice that has the absolute smallest possible length, or Euclidean distance from the origin. In our 2D example, given those long, skewed vectors, 31 to 15 and 17 feigned, finding the vector 1, 0, 1 would be solving SVP for that basis.
Okay, easy in 2D if you know the trick, hard otherwise. What about high dimensions?
In high dimensions, finding the exact shortest vector is known to be NP-hard, which basically means no efficient algorithm is known, and likely none exists. For the hundreds of dimensions used in cryptography, it becomes truly intractable. There are algorithms cryptographers use, like LLL or BKZ, which try to find approximately short vectors, essentially cleaning up a bad basis to make it a bit better. But even these powerful tools struggle immensely and run in exponential time for the parameters needed for security.
So SVP is finding the shortest stick starting from the origin. What about the other one you mentioned, CVP?
Right, the closest vector problem, CVP, is very closely related and maybe more directly relevant to encryption. Given a lattice basis, again, usually a bad one, and a target vector point in space that is not necessarily on the lattice grid.
So a point somewhere between the grid lines.
Exactly. The goal is to find the lattice point, the actual grid intersection, that is closest to that target point.
Oh, like rounding to the nearest grid point, but in hundreds of dimensions where you can't see the grid clearly.
That's a great way to put it. This problem is directly used in many encryption schemes. You can imagine encoding a message by slightly perturbing a lattice point, moving it off the grid to represent the message. The public key is the bad basis and this off-grid target point. The legitimate recipient with their good basis can easily round the target point back to the nearest lattice point, removing the perturbation and recovering the message. But an attacker, lacking the good basis, faces an intractable CVP.
It highlights the core difficulty. For an attacker, it's like searching for a specific grain of sand on an infinite, utterly featureless beach in n dimensions.
Even with powerful tools, the sheer scale and lack of obvious structure makes it effectively impossible.
And this hardness, crucially, extends even to quantum computers, right? That's the whole point of PQC.
Absolutely. The fundamental reason these problems, SCP and CVP, are believed to be hard even for quantum computers is that they seem to lack the specific kind of mathematical structure, like the periodicity. Shor's algorithm exploits that quantum algorithms are known to be good at finding. Lattice problems feel more like complex, messy geometric searches rather than neat algebraic patterns. The best-known algorithms for solving them, whether classical or quantum, have runtimes that grow exponentially with a dimension n.
So that exponential growth is our shield.
It's our crucial advantage. To stay ahead of any future computational power increases, classical or quantum, we can simply increase the number of dimensions in our lattice. Making the problem exponentially harder ensures long-term security.
Okay, so these abstract mathematical grids in high dimensions are powerful, but how do we make them practical for actual computers? I mean, working with infinite grids and potentially huge numbers sounds computationally expensive. How do we keep things manageable?
That's a very practical question, and it brings us to two key mathematical tools that are essential for making lattice crypto work in the real world. First, modulo arithmetic.
Clock arithmetic, like 13 o'clock is 1 o'clock.
Exactly. Instead of dealing with an infinite range of integers, we can find all our calculations to a finite set. If we say we're working modulo dollar, it means after any addition or multiplication, we only care about the remainder when the result is divided by dollars. So $18 p mod 7 equals 44, just like you said. This effectively wraps our infinite space around into a finite, manageable structure. Geometrically, it's like turning the infinite grid into the surface of a torus or a donut. But crucially, it does this while preserving the essential local lattice structure and the hardness of the underlying problems.
And this is important for fixed key sizes.
Vital. It allows us to create cryptographic schemes where keys, messages, and ciphertext all have fixed, predictable sizes, which is absolutely necessary for practical systems and protocols. We call these co-Rayleigh lattices.
Okay, so modulo arithmetic keeps the numbers bounded. What's the second tool? It relates to that error or noise you mentioned earlier.
Precisely. The second key ingredient is the careful use of Gaussian distributions to add noise or error, specifically a discrete Gaussian distribution.
Okay, Gaussian like the bell curve, but discrete.
Right. Think of a bell curve centered at 0, but instead of a continuous curve, you only sample integer values with probabilities highest near 0 and dropping off quickly as you move away. When we encrypt a message, for instance, we don't just land exactly on a perfect lattice point. We often compute a lattice point related to the message and then add a small error vector where each component is drawn randomly from this discrete Gaussian distribution.
So you deliberately nudge the point slightly off the grid.
We do. The distribution ensures these errors are typically very small, so the resulting point doesn't stray too far from its intended lattice location. This allows the legitimate user, who knows the secret structure, the good basis or equivalent secret, to easily correct for this small error to round back to the original lattice point and recover the message. But, crucially, this small amount of controlled randomness is sufficient to obscure the true underlying lattice structure from an attacker who only sees the noisy, off-grid point. It essentially hides the signal within the noise.
So modulo arithmetic gives us finite spaces, and carefully added Gaussian noise lets us hide secrets without losing them. These really are the fundamental concepts, the secret ingredients that make these abstract mathematical ideas not just secure, but actually practical for our digital world. Hashtag tag the core engines of lattice cryptography. All right, so we've laid the groundwork. Lattices, these hard problems like SVP and CVP, the clever trick of good versus bad bases, and these essential tools like modulo arithmetic and Gaussian noise. Now, how do cryptographers actually build practical security systems out of these pieces? You mentioned LWE as a real game changer earlier. What makes learning with errors so revolutionary?
Indeed. While SVP and CVP are the fundamental theoretical bedrock, directly building crypto systems on them can be a bit cumbersome and maybe less flexible than we'd like. That's where learning with errors, LWE, introduced by Oded Rija back in 2005, was a truly revolutionary breakthrough. It's often called the cornerstone or the workhorse of modern lattice-based cryptography. Why? Because it's much more versatile for building schemes, yet its security is provably linked back to the hardness of those fundamental worst-case lattice problems like SVP.
Okay, so it gives you flexibility and that strong security guarantee. How does this LWE game work? Give us the simple version.
Let's simplify it. Imagine an oracle, like a black box, that knows a secret vector vectors, just a short list of small, secret integer numbers, modulo. You, as the challenger, can ask the oracle for samples. For each sample you request, the oracle first generates a random vector vector, also modulo dollar. It computes a hidden value by taking the dot product. Then, and this is the crucial part, it adds a small random error drawn from that discrete Gaussian distribution we talked about to this hidden value. Let's say vex plus a p mod q. Finally, the oracle gives you the pair. The LWE problem is this. Given many, many such noisy samples, can you figure out the original secret vector? Ah, so if there were no errors, no E, it would just be solving a system of linear equations. High school algebra, basically. Exactly. Trivial for a computer. But those small, carefully chosen errors, that Gaussian noise, make it incredibly difficult to disentangle the true secret vex from the randomness. The noise hides the secret signal.
And the why it's hard part. You mentioned this connection back to the fundamental lattice problems. How does that linkage provide so much confidence?
This was Rijiv's really profound contribution. He proved what's called a worst case to average case reduction. It essentially shows that if you could create an algorithm that solves the LWE problem efficiently on average, meaning for typical random instances, then you could use that same algorithm as a subroutine to solve the worst-case hard instances of certain lattice problems, like gap SVP, a decisional version of SVP.
Wow. So breaking average LWE means breaking the hardest known lattice problems.
That's the implication, yes. It provides immense confidence in LWE security, even against quantum computers, because we strongly believe those worst-case lattice problems are genuinely hard. It means we don't have to worry about attackers finding some easy subset of LWE instances to crack. If any significant fraction are easy, they're all easy, which implies the underlying lattice problems are easy, which we think is extremely unlikely.
That's a powerful guarantee. But you mentioned a drawback, practical drawback.
Yeah, the main practical drawback of the original LWE formulation is that the public keys can become quite large. Essentially, a public key might consist of many of those sub-AMI samples.
So lots of vectors and numbers.
Right. This impacts key sizes, ciphertext sizes, and potentially computation speed, which isn't always ideal, especially for constrained environments.
Okay, so LWE is powerful and secure, but potentially bulky. To make things more efficient, cryptographers then developed ring learning with errors, or RLWE. What does the ring part add?
Correct. RLWE was developed specifically to address the efficiency limitations of LWE. It does this by introducing extra algebraic structure, moving from vectors of numbers to operations within mathematical structures called polynomial rings.
Polynomials.
Yeah.
X bar 2 plus bx plus c.
Exactly like those, but often with many more terms, up to degree 1 adult ones. Instead of working with vectors of individual numbers modulo figure, RLWE works with these polynomials, whose coefficients are numbers modulo dollars. All the calculations, additions, multiplications are done with these polynomials, and the results are taken modulo dollars for the coefficients, and also modulo a specific polynomial, typically 6 dollars plus moments where another dollars is a power of 2. This creates a highly structured algebraic ring.
So the RLWE game is similar to LWE, but everything's a polynomial now.
Pretty much. The secret eggs, the random element, the error, they're all polynomials. A sample you receive is a pair of polynomials where bx plus ax, with all operations happening in this polynomial ring structure, modulo $1 and $6 plus other.
And the efficiency gain here is substantial, I gather. How does working with polynomials help so much?
It's a massive gain. A single RLWE sample involving just 2 polynomials effectively bundles the equivalent information of LWE samples.
Yeah.
This drastically reduces the size needed for public keys and ciphertexts. Furthermore, polynomial multiplication in these specific rings can be done incredibly quickly using algorithms related to the fast Fourier transform, FFT, specifically the number theoretic transform, or NTT. This speeds up computations dramatically.
So you get smaller keys and faster operations.
Generally, yes. This is where that mathematical elegance really shines. Adding this ring structure gives us huge efficiency improvements, seemingly without sacrificing the underlying hardness assumption related back to lattice problems.
But life's rarely perfect. Was there a catch with RLWE? Maybe a security concern with all that extra structure?
There were some theoretical concerns, yes. That extra structure, while great for efficiency, might potentially offer an attacker some additional mathematical levers to pull, although no concrete attacks have materialized against well-chosen parameters. It also makes some advanced applications a bit trickier. This led to a sort of compromise.
The Goldilocks solution. Not too unstructured like LWE, not too structured like RLWE, but just right. That must be module learning with errors, or MLWE.
Exactly. MLWE is a fantastic hybrid, emerging as a Goldilocks solution that nicely balances the security robustness of LWE with much of the efficiency of RLWE.
How does it achieve that balance?
Instead of working with single polynomials, like RLWE, or vectors of plain numbers, like LWE, LWE works with vectors of polynomials. So the secret key defects in the random element vector are now vectors, maybe of size collars, where each component is itself a polynomial from that ring we discussed. A sample then consists of a vector of polynomials devec and a single polynomial dollars, where dollars is approximately equal to the inner product vex, again with a small polynomial error added.
So you have k polynomials in your vectors instead of just one. What does that buy you?
Flexibility. It allows cryptosystem designers to choose the dimension tupelers of these vectors, typically small values like KOT2, $3, or 44, to tune the trade-off. Increasing error slightly increases security confidence, closer to LWE, at the cost of some size speed, while smaller dollars is closer to RLWE's efficiency. This ability to fine-tune, offering this best of both worlds balance between security and performance, is precisely why MLWE became the foundation for NIST's primary standardized algorithms. CRYSTALS-Kyber for key exchange, ML-KEM, and CRYSTALS-Dilithium for digital signatures, ML-DSA.
It's like finding that just right sweet spot on the dial, giving us the robust security guarantees close to LWE with much of the practical speed and compactness benefits from RLWE. Makes sense why NIST favored it. Now, what about the other core problem you mentioned earlier, SI? Where does that fit into the engine room?
Right, the short integer solution, SI's problem, it's mathematically related to LWE, often considered its dual problem. While LWE forms the basis for many encryption and KEM schemes like Kyber, SES is particularly well suited for building digital signatures like Dilithium.
Okay, Joule to LWE, good for signatures. What's the size game?
In the SIS game, you're given a matrix dollar. It's typically a wide matrix, say 1 times smaller, where nuller is much larger than an olive, filled with random-looking numbers. Modulo. Your goal is to find a non-zero integer vector velt of length dollar, such that 2 conditions hold. First, dollar times velar equals a 0 vector, all modulo velar. Second, the vector vel must be short, meaning its components, the individual numbers inside it, must be small, typically just small integers like -1, 0, 1, bounded by some small value.
So finding any solution Vilta-Development is easy linear algebra.
Correct. Because the matrix allows a dollar, there are tons of solutions. That part's easy.
But finding a short solution, one where the numbers in Velit are all small, that's the hard part.
Precisely. Finding any solution is straightforward, but those solutions will almost always have large, seemingly random components. Finding one where all the components of say are small integers is believed to be incredibly difficult. It's like searching for a tiny specific needle, a short solution, and a huge haystack of much larger, less useful needles, long solutions.
And this connects back to lattices, too.
Yes, the SIS problem is equivalent to finding a short vector in a specific lattice defined by the rows of the matrix dollars. So its hardness is also rooted in the presumed difficulty of lattice problems. Its application in digital signatures is quite natural. It provides a basis for building cryptographic hash functions, or more directly, one-way functions. It's easy to compute a VETSI if you know VETSI, but given a DACO in the result, which is VETSI in the SIS problem itself, but can be something else in signature schemes based on it, it's hard to find a short VETS that produces that result. This forms the core security idea behind CRYSTALS-Dilithium.
Got it.
The beauty of all these problems, LWE, RLWE, MLWE, SIS, is their deep interconnectedness. They're variations on a theme of finding short or close vectors in lattices, or dealing with noisy linear equations. Strong evidence for the hardness of one often bolsters confidence in the others, strengthening our belief in their collective resilience against both classical and, crucially, quantum attacks. Constructing crypto systems from theory to practice.
Okay, so we've got these powerful mathematical engines, LWE, RLWE, MLWE, and SIS, all humming along based on the hardness of lattice problems. How do we actually take these engines and build the practical cryptographic tools we need every day, like secure communication for online banking, or digital signatures to verify software downloads? How do we get from theory to practice?
That's the next crucial step. Constructing actual crypto systems. Let's start with public key encryption, PKE, and more specifically in this post-quantum context, key encapsulation mechanisms, or KEMs. Now, traditional TKE allows anyone with your public key to encrypt a message that only you can decrypt with your private key. But in modern secure communication protocols like TLS, which secures HTTPS web traffic.
Right, they don't encrypt the whole conversation with the slow public key stuff.
Exactly. It would be way too slow. Instead, they use a hybrid approach. The slower asymmetric PKE, or now a PQC equivalent, is used just once, right at the beginning of a connection, to securely agree on a short, shared symmetric key. Think of it like securely exchanging a temporary password.
And then that symmetric key, using something fast like AES, encrypts all the actual data flowing back and forth.
Precisely. Symmetric crypto, like AES, is orders of magnitude faster. So a KEM is a specialized type of PKE designed exactly for this task, establishing their shared symmetric secret. It typically has 3 core algorithms. KEGAN creates a public key and a private key. INCAP key takes the recipient's public key, generates a fresh symmetric key, let's call it CKSS for shared secret, and produces a ciphertext, which encapsulates SYSIPA, sends signed to the recipient. TCAPs CANTE. The recipient uses their private key and the received ciphertext setup to recover the exact same shared secret.
And the security goal is critical. An eavesdropper seeing the public key PKK and the ciphertext data should have no way to figure out the shared secret cyber.
That's the core security property, known as IND-CCA2 security, usually.
Okay, and the NIST standard KEM, the primary winner of their competition, is CRYSTALS-Kyber, now officially called ML-KEM. Let's do a bit of a deep dive into how Kyber actually works. Without getting lost in the polynomial math, what are the basic steps?
Okay, let's sketch it out. Kyber is based on the module learning with errors, ML-WE problem we discussed, using vectors of polynomials. It comes in different security levels. Kyber 512, 768, 1024, corresponding roughly to AES 128, 192, 256 security against quantum attackers. Let's think about the 3 steps. First, Kyber KEGAN. To generate your key pair, the system essentially creates that public scrambled map of the lattice based on ML-WE. It starts by generating a public matrix mathBFSD consisting of random-looking polynomials. Then it generates your secret key mathBFS, which is a vector of small polynomials, small coefficients. It also generates a small secret error vector mathBFS. Your public key mathBFT is then calculated as mathBFA plus mathBFE. So mathBFT is derived from the secret mathBFSE, but masked by multiplication with mathBFA and the addition of noise mathBFT.
So again, the public key mathBFT looks like a noisy scrambled version related to the secret mathBFT, making it hard to reverse and find mathBFT. Got it. Now, how does someone use my public key mathBFT and to send me a shared secret? That's the INCAPS step.
Right, Kyber INCAPS must PK. When someone, let's call them the sender, wants to establish a shared secret with you, they use your public key. First, they generate their own temporary secret randomness. A vector, mathBFU, made of small polynomials, and some small error polynomials, mathBFU and DFT2. They then compute 2 ciphertext components, let's call them mathBFU and V. MathBFU is calculated roughly as mathBFT, mathBFU2. Here, mathBFU is a small random message, the seed for the shared secret, and code essentially scales it up and adds it into the mix, often near the middle of the Module-LWE range. The final shared secret center is derived by hashing this random message mathBFT. The ciphertext that the sender sends to you is just the pair.
Okay, so the sender mixes their randomness, mathBFU1, E22 with my public key, mathBF2, and the secret seed mathBFTF to get the ciphertext mathBFU. Now I receive mathBFU. How do I, the recipient, use my private key mathBFE to get back that original mathBFE and thus the shared secret SS? This is the decap step where the magic must happen.
This is indeed the crucial step, Kyber decaps, and it really shows how that controlled noise works for us. When you receive matchBFU dollars, you use your private key, mathBFU. You compute a value simply by calculating mathBFUs. Now let's think about what vibes from the ciphertext and your calculated dollar represent, without writing out all the terms. If you substitute the definition of mathBFU into ViveBFU and also substitute the definition of mathBFT into the sender's calculation of dollars, you find something remarkable. The difference, BFU, boils down almost entirely to a combination of the small error terms introduced by the sender, mathBFE22, and the original error mathBFE from your public key, all multiplied by small secret values, mathBFU and mathBFUs.
Ah, so because all those secret vectors and error terms were deliberately chosen to be small, their combinations are also small. The difference value is tiny.
Exactly. The difference ViveBOLE is a known small error value. Because the original message seed MathBSA was encoded by adding it near the middle of the range, like adding 2 draws 2, this small difference means that VIVE-LWE and your calculated $5 are close enough in the modular arithmetic. You can compute CVAL-V and reliably check if it's closer to 0 or closer to that 2K2 offset. This allows you to deterministically remove the noise and recover the original message seed MathBFA. You then hash MathBFA just like the sender did, and voila, you arrive at the exact same shared symmetric secret homologous.
That is clever. The noise is just enough to confuse an attacker who doesn't have S, but small enough that the legitimate recipient with S can cancel it out and find the signal M.
Precisely. For an attacker without MathBFA, the ciphertext MathBFU-BBA looks essentially like random values related by an unknown, noisy linear equation. It's an MLWE problem since they can't solve.
This is where the noise becomes not a bug, but a feature allowing us to hide secrets in plain sight. Amazing. Okay, that covers encryption key exchange with Kyber. Now what about digital signatures? Equally critical for proving authenticity and integrity.
Absolutely. Digital signatures provide authenticity, proving who sent something, integrity, proving it wasn't tampered with, and non-repudiation, preventing the sender from later denying they sent it. They are the bedrock of trust for software, documents, transactions. So much of our digital world. A digital signature scheme typically involves 3 algorithms. Keygen, to create the public privatization and signing keys. Sign message, which uses the private signing key to produce a signature signal on a message, and verify, PK message sigma, which uses the public verification key to check if the signature sigma is valid for the given message.
And for this crucial task, NIST's primary choice is CRYSTALS-Dilithium, now officially ML-DSA. You mentioned it's based on Module-LWE and uses this intriguing fiat-Shamir with aborts technique. How does dilithium work? That, with aborts part, sounds particularly interesting.
Dilithium's Keygen is conceptually quite similar to Kyber's, actually. It also uses MLWE for part of the key. You generate a public matrix MathBFA of the polynomials. You generate 2 secret vectors of small polynomials, MathBFS21. Your public key includes MathBFA and a vector, MathBF2, calculated as MathBFE, MathBFS2. Your private key is the pair, MathBFS2. Now, the sign message process is where the fiat-Shamir with aborts comes in. It's a clever protocol designed to be zero knowledge in a sense, proving you know the secret key without revealing it. Here's the flow. 1. Commit. The signer first generates a random masking vector, MathBFI, made of polynomials with coefficients in a certain range. This MathBFY acts as a temporary one-time secret. They compute a commitment value, MathBFA, by multiplying the public matrix MathBFA2. Think of MathBFA as sealing the randomness MathBFY in an envelope. 2. Challenge. Next, a challenge value is created. It's derived by hashing the message being signed together with the high-order bits of the commitment on math. This hash value CCAD is essentially a random-looking challenge that depends on both the message and the specific commitment.
Okay, so the challenge CATAR is tied to the message and the commitment MathBF2. Then the signer has to respond to this specific challenge.
Yes. 3. Response. The signer computes a response vector, MathBFC, by combining their temporary secret MathBFMA with their long-term secret key, MathBFA, scaled by the challenge C2. So MathBFA plus C is the FAC, though. This MathBSA essentially opens the commitment in a way that's related to the secret key in the specific challenge. But here's the absolutely crucial step. 4. Rejection sampling, the abort step. Before outputting the signature, the signer meticulously checks the size of the coefficients in the calculated response of MathBFC, and also another related value involving MathBFC. They must fall within very strict predefined bounds. If any coefficient is too large, the signer aborts the entire signing attempt and restarts from step 1 with a completely new random MathBFC.
Wait, they just throw it away and start over if the numbers get too big. Wait, doesn't that waste time?
It might seem inefficient, but it's fundamentally critical for security. This rejection sampling ensures that the distribution of the final signature of MathBFC all day that gets released reveals absolutely no information about the signer's secret key MathBFSD or MathBFS2. If large coefficients were allowed, their statistical properties could leak information over many signatures. The abort step prevents this leakage. It happens with reasonably high probability that a signature attempt will pass the checks eventually.
So the abort step is basically the algorithm saying, oops, that signature attempt might accidentally reveal a tiny bit about the secret key because the numbers got too big by chance. Let's scrap it and try again with fresh randomness.
That's fascinating. A built-in self-censoring mechanism for security.
That's a great way to think about it. It's a brilliant dance between randomness, the fresh math BFC each time, and a strict adherence to output bounds, ensuring the mathematical security proof holds up in practice. If the checks pass, the final signature sigma is the pair. Okay, so that's signing. How does the verify message sigma step work? How does someone check this BSDZ $1 pair?
The verifier has the public key math BFT, the original message, and the signature sigma. They essentially try to reconstruct the signer's commitment, math BFTA, using the public information. They compute a value, math BFT, the country of mate. Now, if you substitute the definition of math BST and math BFT into this equation and simplify, you find that math BFT should be equal to math BFPF tree. This is very close to the signer's original commitment, math BFT, math BFY, differing only by that small term involving math BFS2 and math Y. The verifier then performs two critical checks. Check 1, challenge consistency. They take their computed math BFTT, extract its high-order bits, and hash them together with the message, just like the signer did. They check if this recomputed hash matches the challenge suscited in the signature. If it doesn't match, the signature is invalid. Check 2, bound check. They check if the coefficients of the vector math BFC from the signature are all within the same strict bounds that the signer had to adhere to during rejection sampling. If any coefficient is too large, the signature is invalid.
So they check if the challenge makes sense given the response, and they check if the response itself looks like it came from a legitimate signer who followed the rules, stayed within bounds. If both pass.
If both checks pass, the signature is declared valid. Forging a signature that passes both checks would require being able to find a short vector math BSC satisfying the verification equation, which is essentially solving the hard module SIS problem underlying dilithium security.
Wow. That rejection sampling really is key, both for the signer to avoid leaking secrets and for the verifier to confirm the signature's legitimacy. Dilithium comes in security levels 2, 3, 5, right, with signature sizes around 2 to 4 kilobytes.
That's correct. Roughly 2.4 KEB for level 2, up to about 4.6 KBB for level 5. We should also briefly mention Falcon, the other NIST-deflected lattice signature. It's based on SIS over different structures called NTRU lattices. Its main advantage is significantly more compact signatures, but is generally considered more complex to implement securely due to its use of floating-point arithmetic during signing. Dilithium's reliance on integer arithmetic is often seen as an implementation advantage. Hashtag of real-world standardization, implementation, and challenges.
We've covered the what and the how of these amazing lattice algorithms. Now let's talk about the when and the where. Having great algorithms on paper is one thing, but getting them deployed safely across the entire globe, protecting literally trillions of dollars in e-commerce, securing government communications, safeguarding billions of people's data, that's a whole different kind of challenge. The NIST post-quantum cryptography standardization process was clearly a pivotal moment. What was the real-world story behind that massive effort?
It truly was an unprecedented multi-year global undertaking. NIST recognized the quantum threat relatively early, and starting in 2016, they launched a formal, public, transparent process to solicit and rigorously evaluate candidate algorithms from researchers worldwide. It wasn't something done behind closed doors.
More like a marathon than a sprint, you said?
Definitely. In 2017, they received 69 valid submissions for round 1. The global cryptographic community, academics, industry researchers, government agencies then spent years trying to break these candidates. They meticulously analyzed every mathematical detail, benchmarked performance, probed for potential side-channel vulnerabilities, everything. By 2019, after intense scrutiny, they narrowed the field down to 26 algorithms for round 2. Then in 2020, it was down to 7 finalists and 8 alternates for round 3. It was an incredibly rigorous, open, and absolutely essential process to build confidence.
That really was a global cryptographic Thunderdome, wasn't it? Years of the best minds trying to find flaws in each other's work. So after all that intense evaluation, who emerged as the winners announced in July 2022, and what did that announcement really signal about lattice-based cryptography?
Absolutely. The first 4 algorithms chosen for standardization were: for key encapsulation mechanisms, KEMs, the primary choice was CRYSTALS-Kyber, now officially standardized as ML-KEM. For digital signatures, the primary choice was CRYSTALS-Dilithium, standardized as ML-DSA. They also selected Falcon as an alternative signature scheme, noted for its smaller signature sizes but greater implementation complexity. And they included since founds plus RLWE, which is a hash-based signature scheme. It offers different security assumptions based only on the hardness of cryptographic hash functions, making it a valuable backup with a completely different mathematical foundation.
So Kyber, Dilithium, Falcon, 3 out of the 4 are lattice-based.
Exactly. That fact alone signifies the extremely high confidence that the global cryptographic community and NIST ultimately placed in the security, performance, and versatility of lattice-based approaches. It was a massive endorsement.
A huge vote of confidence, no doubt. But taking these winning algorithms from the NIST standards documents and getting them implemented correctly and efficiently in every computer, phone, server, smart card, and IoT device on the planet, that must come with some significant practical challenges, right? Especially around things like key sizes. I've heard they're quite a bit bigger than what we're used to.
You've hit on probably the most immediate and widely discussed practical challenge, the size problem. Compared to the elliptic curve cryptography, EC we commonly use today, the public keys, private keys, and ciphertexts or signatures for these new PQC schemes are substantially larger.
How much larger are we talking?
Well, for example, a standard ECC public key might be around 32 bytes, maybe 64 bytes for a signature. For Kyber 512, the lowest security level, the public key is around 800 bytes, and the ciphertext is about 768 bytes. For Dilithium 2, the lowest level, the public key is roughly 312 bytes, and the signature is about 2,420 bytes.
Okay, so we're talking roughly a 20x to 40x increase in size compared to ECC. That's not insignificant, especially if you think about tiny IoT devices sending data or even just the overhead and TLS handshakes affecting web page load times.
It isn't insignificant at all. While it's generally considered manageable for many standard internet protocols like TLS, where this larger key exchange happens only once at the beginning of a connection, it can definitely be a serious issue for resource-constrained environments. Think smart cards with very limited memory, tiny embedded sensors, or systems operating over very low bandwidth networks. Could impact network latency and performance.
So size is a definite hurdle, but what about speed? Are they slower too?
Interestingly, no. That's the surprising and very positive flip side. In terms of performance, these lattice-based schemes are often remarkably fast on modern CPUs. For many operations like key generation, decapsulation, and signature verification, they frequently outperform classical RSA and even ECC.
Really? Faster, even though the math sounds more complex. How?
It comes down to the nature of the core operations. They primarily involve additions and multiplications of polynomials. These operations are highly parallelizable, meaning different parts of the calculation can be done simultaneously. And, as we mentioned with RLWE, they are extremely well suited for highly optimized algorithms, like the number theoretic transform, NTT, for fast polynomial multiplication. So while the underlying concepts might be more abstract, the actual arithmetic is very efficient on modern hardware. This excellent performance was a major factor in their selection by NIST, helping to offset the concerns about size.
So they're bigger, but surprisingly faster in many cases. That's a crucial trade-off. But what about attacks that don't target the math itself, but rather how the algorithm is implemented on a physical device? I've heard the term side-channel attacks thrown around. What are those, and are lattice schemes vulnerable?
That's another absolutely critical challenge for real-world deployment, and one that requires immense care from implementers. Side-channel attacks don't try to break the underlying mathematical hardness of the lattice problems. Instead, they exploit information that unintentionally leaks from the physical execution of the algorithm on a piece of hardware.
Leaks? Like how?
It could be through various channels. For instance, timing attacks. An attacker might precisely measure how long certain operations take. If the time varies even slightly depending on secret data, like a bit of the private key, they might be able to deduce the secret over many observations. Or power analysis. Attackers monitor the minute fluctuations in the device's power consumption while it's doing cryptographic calculations. Different operations, or operations on different data, consume slightly different amounts of power, potentially revealing secret bits. There are other channels too, like electromagnetic emissions or even sound.
And that rejection sampling step in Dilithium, the abort step we talked about, that sounds like a prime target for a timing attack. If an attacker could somehow figure out how many times the signing process aborted.
That's exactly the kind of vulnerability implementers need to prevent. If an attacker could reliably count the number of aborts for a given signature generation, it could indeed leak information about the secret key math BFSS. The primary defense against almost all side-channel attacks is to implement the cryptographic algorithms in constant time. This means ensuring that every operation takes the exact same amount of time, consumes the same amount of power, follows the same sequence of instructions, accesses memory in the same patterns, regardless of any secret values being processed.
That sounds incredibly difficult to achieve in practice.
It is. It's a major implementation challenge, requiring deep expertise in both cryptography and low-level hardware-software interaction. Writing custom timecode is notoriously tricky and requires careful design and rigorous testing. It really underscores that the transition to PQC isn't just about choosing the right mathematical algorithms. It's equally about the nitty-gritty, painstaking engineering effort needed to ensure that theoretical security translates into practical, robust security in real-world systems.
Okay, so we're building these incredible new lattice-based defenses, but we can't just deploy them and assume we're safe forever. The future is uncertain, new attacks might be discovered, maybe even beyond quantum computing. This is where concepts like crypto agility and hybrid modes come in, right? It sounds like planning for the unexpected, future-proofing our security posture.
Precisely. We learned hard lessons from past cryptographic transitions. We absolutely cannot predict what future cryptanalytic breakthroughs might occur, or even what new computational paradigms might emerge decades from now. So modern systems need to be designed with crypto agility in mind.
Meaning you can swap out the algorithms easily.
Essentially, yes. Crypto agility means designing systems and protocols so that the underlying cryptographic algorithms, like the KEM or signature scheme, can be easily replaced or updated without requiring a massive overhaul of the entire system architecture. It allows for smoother transitions if a vulnerability is found or if stronger algorithms become necessary. And for the immediate transition period, as we deploy these new PQC algorithms, the widely recommended strategy is to use a hybrid mode.
How does hybrid mode work? You're running both the old classical crypto and the new post-quantum crypto at the same time. That really sounds like a belt and suspenders approach.
That's exactly what it is. It's a very prudent belt and suspenders strategy designed for maximum safety during this transition. When establishing a secure channel, like in TLS, the systems perform two independent key exchanges in parallel. One uses a well-established classical algorithm, like elliptic curve Diffie-Hellman, ECDH. The other uses one of the new PQC chems, like Kyber, ML-KEM. Both exchanges produce a shared secret. These two secrets are then cryptographically combined, actually concatenated and hashed, to produce the final symmetric key used for the session.
Ah, so you get the best of both worlds security.
Precisely. The resulting connection is at least as secure as the traditional classical algorithm. So if, hypothetically, the PQC algorithm had an unexpected flaw, you're still protected by ECC. And it's also at least as secure as the PQC algorithm. So if a quantum computer arrives tomorrow and breaks ECC, you're protected by Kyber. It provides security against both classical and quantum adversaries, making it the safest way to gradually roll out PQC.
And we're actually seeing this hybrid approach being deployed now.
Yes, absolutely. Major players like Cloudflare and Google have been experimenting with and deploying hybrid post-quantum key exchange in TLS for some time now. And with NIST finalizing the standards, FIPS 203 for ML-KEM Kyber and FIPS 204 for ML-DSA Dilithium, implementations are rapidly appearing in critical open-source cryptographic libraries like LibOx, part of the Open Quantum Safe project, and others, paving the way for broader adoption.
It really is about building these future-proof systems, making sure we're not caught flat-footed no matter what new discoveries or threats emerge down the road. That kind of foresight is crucial. #tag the frontier advanced lattice cryptography. Okay, we spent a lot of time on how lattices are shoring up the absolute fundamentals of our digital lives. Secure communication with chems like Kyber and authenticity with signatures like Dilithium. But you hinted earlier that the versatility of lattices extends even further into really advanced, almost science fiction-like territory. You mentioned the holy grail of cryptography, fully homomorphic encryption, or FHE. What makes FHE so revolutionary?
FHE is truly a transformative technology, one that cryptographers dreamed about for decades. It promises a fundamental paradigm shift for data privacy and secure computation. Imagine this scenario. You have highly sensitive personal data, maybe detailed medical records or proprietary financial information. You want to use a powerful cloud service to perform complex analysis or machine learning on this data, but you absolutely do not want the cloud provider, or anyone else for that matter, to ever see your raw, unencrypted data.
Which is the standard problem with cloud computing today. You often have to decrypt data to process it.
Exactly. But FHE allows you to do the seemingly impossible. You first encrypt your sensitive data using an FHE scheme. Then you send the encrypted data to the cloud. The cloud service performs the desired computations, analytics, model training, whatever, directly on the encrypted data without ever needing the decryption key. The result of this computation remains encrypted. The cloud sends the encrypted result back to you. Only you, using your private FHE key, can decrypt the result to get the final answer in plain text. And crucially, that answer is the same as if the computation had been performed on the original unencrypted data.
Okay, that does sound like magic. It's like that locked glove box analogy you hear sometimes. The worker can manipulate materials inside the lockbox using built-in gloves, following instructions, without ever seeing the materials directly. You, the owner with the key, unlock the box later to get the finished product.
That's a perfect analogy. It allows computation without demanding trust in the entity performing the computation regarding data confidentiality. It enables privacy-preserving computation on an unprecedented scale.
But it sounded impossible for a long time. How did lattices make it feasible?
It did seem impossible. Early theoretical constructions existed, but they were wildly impractical. The breakthrough came in 2009 with Craig Gentry's scheme, which was based on ideal lattices. And indeed, essentially all practical FHE schemes developed since then are built upon the foundations of the learning with errors, LWE problem. The main challenge technically for building FHE from LWE is managing that inherent noise or error. Remember how in LWE each ciphertext has a small amount of noise? Well, every time you perform a computation, like adding or multiplying two encrypted values, the noise in the resulting ciphertext grows.
So after too many computations, the noise would just overwhelm the actual data.
Exactly. The noise would grow so large that decryption would fail. The magic of modern FHE schemes lies in a technique called bootstrapping. Bootstrapping is a remarkable process where the scheme can take a noisy ciphertext and essentially refresh it, reducing the noise back down to a manageable level without decrypting it. It's like homomorphically running the decryption circuit itself. This allows for an essentially unlimited number of computations to be performed.
Bootstrapping sounds incredibly complex. Is FHE actually practical today?
It's still computationally intensive, much slower than operating on unencrypted data. But lattice-based FHE has made incredible progress. It's moved from purely theoretical to being practical enough for niche applications. We're seeing pilot projects and specialized uses in areas like secure cloud computing for regulated industries, finance, healthcare, privacy-preserving machine learning, secure database queries, and more. It remains a major area of active research, constantly getting faster and more efficient. It really raises an important question. What previously impossible services could become standard, everyday technologies once FHE matures further?
The potential is staggering, allowing computation without ever seeing the underlying data. The privacy implications alone are mind-boggling. And FHE isn't the only advanced cryptographic tool that lattices enable, is it? You mentioned others.
Not at all. Lattices provide this wonderfully rich mathematical structure that serves as an elegant and efficient, a remarkably unified framework for building a wide array of advanced cryptographic primitives, all with potential quantum resistance. For instance, attribute-based encryption, or ABE.
Attributes, like user characteristics.
Exactly. In ABE, decryption keys aren't tied to a single user identity, but rather to a set of descriptive attributes, like role, doctor, department, cardiology, location, hospital A. Ciphertexts are also encrypted under an access policy defined over attributes, e.g. decryptable by any user who has doctor in cardiology or chief of medicine. You can only decrypt if the attributes associated with your key satisfy the policy embedded in the ciphertext.
That sounds like incredibly fine-grained, flexible access control, much more dynamic than traditional methods. What about zero-knowledge proofs? They always sound like something straight out of a spy movie.
Zero-knowledge proofs, ZKPs, are another incredibly powerful application where lattices shine. A ZKP allows one party, the prover, to convince another party, the verifier, that they know a secret value, or that a certain statement is true, without revealing absolutely anything about the secret value itself or any other information beyond the truth of the statement.
Like proving you're over 21 without showing your birth date, or proving you know a password without sending the password.
Exactly those kinds of scenarios. Lattices are now being used to construct highly efficient ZKP systems that are also believed to be resistant to quantum computers. These quantum-resistant ZKPs are crucial for future applications in privacy-preserving identity verification, secure electronic voting systems, verifiable computation, and even some advanced blockchain and cryptocurrency applications. Beyond these, lattices also provide efficient constructions for things like group signatures, where you can sign anonymously on behalf of a group, identity-based encryption, where your public key can be something convenient like your email address, anonymous credentials, and more. They're expanding the toolkit of cryptography across virtually every digital sector imaginable.
It really is like finding a universal translator or a master key for advanced cryptography, unlocking possibilities and providing quantum-resistant solutions for concepts we once only dreamed of. That's quite a testament to the power hidden within these high-dimensional grid structures. Hashtag, tag, outro. We've certainly covered a lot of ground today. We've journeyed from the edge of that looming quantum cliff where algorithms like Shor's threaten to unravel our current encryption, through the abstract, almost mind-mending elegance of high-dimensional lattices, and deep into the nuts and bolts of the very algorithms that are actively being deployed to build our post-quantum digital future. We started by confronting that chilling harvest now, decrypt later threat, a truly unsettling prospect that makes protecting data today against future attacks absolutely critical. We then discovered lattice-based cryptography as the leading contender, offering not just resilience, but a new, incredibly versatile paradigm for security. We peeled back the layers to understand its mathematical foundations, what a lattice actually is, the ingenious difference between good and bad bases acting as the core secret, and why problems like the shortest vector problem, SVP, and closest vector problem, CVP, are believed to be so incredibly hard even for powerful quantum computers.
And from those foundations, we explored the core engines driving modern lattice crypto. The learning with errors, LWE problem, and its crucial, more structured variants, Ring-LWE and Module-LWE, which balance security and efficiency. And also the dual problem, the short integer solution, SIS problem. These are the mathematical workhorses allowing us to construct practical systems.
Right. And then we saw how these engines power the new NIST standardized algorithms that are leading the charge. CRYSTALS-Kyber, ML-KEM for key exchange, and CRYSTALS-Dilithium, ML-DSA for digital signatures. We walked through how they work at a high level and saw the clever ways they use controlled noise and techniques like rejection sampling to secure our information.
We then shifted to the real world, discussing the monumental NIST standardization process that selected these algorithms after years of global scrutiny. We confronted the practical challenges, the larger key and signature sizes compared to what we're used to, but also their surprisingly strong performance on modern hardware. And we highlighted the critical importance of addressing side-channel attack vulnerabilities through careful, constant-time implementations.
And we touched on the vital strategies for navigating this transition safely, designing for crypto agility to handle future unknowns, and deploying in hybrid modes as a belt-and-suspenders approach, combining classical and post-quantum methods for maximum security during the rollout.
The strategic importance of this global migration really cannot be overstated. This isn't just a minor update, it's a significant generational upgrade in the history of our digital infrastructure. It's absolutely essential if we want to maintain global digital trust and security in an era where powerful quantum computers are becoming an increasingly tangible prospect.
Yeah.
And importantly, lattice-based cryptography doesn't seem to be just a temporary patch. The mathematics appears to be a robust and incredibly fertile ground for cryptographic innovation, likely to secure our digital world for decades to come, and even enabling previously unimaginable privacy-preserving technologies like fully homomorphic encryption.
So the post-quantum future, it seems, is being built on a lattice, which leads to a final thought for you, our listeners. What responsibilities does this new era of digital security based on these powerful but complex new foundations place on you, whether you're a user, a developer, a policymaker, or simply a citizen of the digital world? What's your role in understanding and demanding these new protections?
That's a crucial point. Knowledge is most valuable when it's understood and applied. As quantum computing continues its advance, the ongoing refinement, rigorous implementation, and widespread deployment of these lattice-based methods will be absolutely critical. This raises an important question for everyone. What steps will you take to safeguard your own digital presence in this evolving landscape, and how might you contribute in your own way to building a more secure and trustworthy digital future for everyone?